was really great, and I grabbed my coffee so I can do stupid things faster. So I'm going to take us down a little bit different path because I'm actually not an ethicist. I'm on the technical side of things, and something that wasn't said as part of my bio is when I was at NCI, I was also the Chief Information Officer for the organization, about 8,500 people, and that really did have me think a little differently about risk and what exposure and what data loss meant to an organization. So what I'm going to do is I'm going to give you the take-homes from my talk before I talk, because I think that way then, one, you can tune out, and then two, I'm just going to be supporting really these ideas in my presentation. First thing is, and again, this is now the technical person speaking, not the ethicist or talking about from a legal standpoint, data really need to be liquid. And I'll talk about what that really means. Data sharing itself needs to scale. And Kim was talking a bit about some of the issues around consent, around what I would call high touch, around making data shareable. And to make those things scale, we really do need to understand, well, how does the system itself accommodate that, and how do we make that happen? I know John Wilbanks is going to talk a lot more than I will about this. In fact, I won't probably talk about it at all. Consent really is a process, and it's we embed things in that process, but really consent itself is something that all of us go through every day in many different contexts. And how do we make that more visible and more appropriate? And then something that I guess I've really lived in the last few years at NCI and now at Duke is particularly in the area of cancer, but I think it's true in many other diseases, is as we move down the precision medicine road, we're realizing that common disease now really is a collection of rare diseases. And that has lots of interesting implications, both from a data standpoint and then from a care standpoint. My last message at the bottom, in some ways, is I think the most important one, and the whole idea of a learning health system, and frankly the whole direction we're trying to move, is we want to learn from the experience and the presentation of every single patient. And that we can debate and should debate exactly how that happens, but the fact that we really do need, as a society, to learn from everyone and improve for the next presentation of a disease is critical. And I think that's why we're all here. So, again, because I'm really been deeply embedded in the cancer world for a long time, I really do think of cancer as a grand challenge. It's certainly not the only one. But when I was at NCI, I had the opportunity to interact with a lot of different agencies, a lot of different groups, and in particular in the physics community, they think about everything as a grand challenge. And I realized that that's actually a useful framework for thinking about cancer. It is a grand challenge. It requires for us to solve problems in a deep biological understanding, so the really deep research into biological underpinnings of disease. And then there's a whole lot of technical pieces, advances in scientific methods, instrumentation, technology, data computation, mathematical models, predictive models. And I think, again, one of the things that's really coming out is that it's access to data that's really critical in creating learning health systems. And that access to data really helps inform how we need to move forward and the changes we need to make to improve care for patients. And improve not just care for patients, but improve the way that we live so we decrease our risk of getting disease in the first place. So I think we can't lose sight of this whole continuum, that a lot of this is also about making sure people don't get sick in the first place. So just to briefly support my idea that, and it's not my idea, the idea that precision medicine's really making cancer in particular a collection of diseases. You can see, sorry, this is a very small slide. Back in 1996, the way that most people thought about a number of major classes of cancer, so non-small cell lung cancer, breast cancer, colorectal cancer, melanoma, prostate was effectively as a single disease. By 10 years later, we were realizing, at least in a couple of those diseases, there were a lot of subtypes. And by last year, in fact, all of them had become subtyped, with the exception of prostate. And now prostate it's clear there are multiple classifications, and you can tell that just from the fact that many patients have indolent disease versus aggressive. That's a classification. We don't know how to classify it yet. So what's happening is that, at least in cancer, we're recognizing that we need to be able to aggregate data across a lot more patients just to understand a single subtype. And again, I think that's a really important part of this. From a soapbox standpoint, I think the other thing that was very interesting for me when I was at NIH is to realize that there's really very little work being done on, well, what is health? What does it mean to be healthy? And how do we measure health? Because in fact, if we could do a better job of measuring what health is, I think we could do a much better job predicting when people are going to be sick. So I can share a number of anecdotes, but because I only have 15 minutes, I won't. One of the most interesting ones, though, is looking at early detection in cancer. And if you try to do too much early detection, you really increase the risk to patients. And I can talk about South Korea and their thyroid cancer issues of looking too much for thyroid cancer if we have time for that. The other thing that's really changed in my mind is a recognition, not just in the clinical team, but now in research, how team science is so important. And it's really building up teams of people that work here. And I realized that I did not put in bioethicists into this framework, and I'm very sorry. I should have gone back and edited this. That's bad on me. But really, the idea of having a whole team around every part of the enterprise is incredibly important. The other thing, and Kim already had a slide that is in some ways more eloquent about this than this one is that the scale in which we're doing research and the scale at which we can operate as a society has dramatically changed. So back in 2001, the Human Genome Project finished the first draft sequence of the human genome. That draft sequence cost roughly $100 million, but the project overall at that point in time was about $3 billion. And I like to use that number because there was a lot of technology development that went on to make the Human Genome Project possible. Fast forward 9 years, and NIH was already talking about doing 1,000 genomes for roughly that same $100 million price tag. Then moving in 5 years later, starting the Precision Medicine Initiative, now All of Us, which is 1 million people. So again, in now less than 5 years, again a tenfold doubling of the number of people that would be participating. And I think, again, one of the challenges is as we start thinking about the technology scaling like this, how do we scale the rest of the interactions around healthcare? And it's clear we haven't figured that out yet. One of the things I feel really strongly about, though, is that we do need to have open science. We need to have open data. You see FAIR, and as I think Katie pointed out, FAIR, or was it Jody? I'm not sure which one of you it was. She pointed out that FAIR, the acronym findable, accessible, interoperable, and reusable, it's how the folks that are doing data science can really use the data in hopefully appropriate and informative ways. And at the end of the day, in my mind, it's about how do we also improve, increase, and amplify innovation. So this is a nice little graph. I'm not going to go into it in a lot of detail from the Harvard Business Review last year in June. And I've found that I didn't used to quote Harvard Business Review in my talks, but now I do. What's really interesting about this is it's talking, there's two axes. One is how complex the data set is. So how rich from a biological standpoint it is, and then how well shared. So sharing is the y-axis, and richness is the x-axis. And you can see there's actually very little of our large data sets, our large projects that are both rich and well shared. And one of those is the MMRF COMPASS study that's up in that upper right-hand corner. So that's an interesting problem for all of us. I think that we're all trying to figure out how do we make much more complex data sets more accessible, so we can learn from them, so we can improve care. I'll just, again, re-emphasize that data liquidity, at least to me, is easiest when the data is generated electronically at the beginning. So that means lab data, sequencing data, all these things are essentially digital when they're born. And what I find really frustrating is we ask our clinicians, our care team, the pathologists, the radiologists, to make notes of something that's actually present in the digital data. And then we spend a lot of time annotating and curating those annotations to make sure they really did represent the raw data. I think we're much better off, and again it goes back to friction of data, if we can have those digital forms of data move rather than the annotations move. And in fact, for us to really apply machine learning concepts in healthcare, we really do need to have more access to that underlying raw data, with all the caveats that Kim already mentioned, that our use of it is not always straightforward and has implications that we don't always see at the time. Part of this, though, is also about humans have limited cognitive ability. So this, oops, yeah, wrong button. Ah, yikes. Now I killed it. Rats. I guess I won't use that button again for the rest of my talk. Thank you very much. So the human cognitive capacity, so our ability to make decisions, really is a fixed number. We can try to massage the information and make it more consumable for us to make decisions on it, but we're not rapidly evolving like, unfortunately, the digital world is. So we need to help people with this ever-increasing burden of data that helps them make decisions. And that's the way, at least I think about things like machine learning applied to imaging. In this particular case, this is Sebastian Thrun and his colleagues now at Google were able to take machine learning and apply it to photos of patients with potential melanoma, and they could do as good a job as the best trained dermatologist at calling out whether or not that was melanoma. It's not to remove the dermatologist, it's actually so they don't have to look at those pictures, and to have more consistency in the way those digital images are handled. So I'm going to wrap this up and say that I believe now really biology and medicine are data-intensive enterprises. Scale for all of us has rapidly changed. I think that's why we're all here talking about learning health systems, healthcare systems. Technology is everywhere. We can't. That's one of the rabbits that we can't put back in the box. And it's really, and again, I think there's some things here we haven't figured out how to do as a society. How do we leverage the fact that I carry accelerometer and a GPS with me everywhere? Is there somebody that can look at my travel patterns and one say, well, he's a little crazy, but two, he's at risk for getting some disease because look, he's changed his sleep pattern, whatever it is, that it would be useful then to be able to get some kind of information back from these devices to say, you know what, take a day off. I'd actually appreciate that anyway. And then just to reiterate, data liquidity in healthcare is really key for us unlocking a lot of the advantages of having these systems in place. And with that, I will stop.